Okay.
Yes, I think.
Okay, fine. I think we have the slides. This is just as usual stuff. Basically, I think last time we left on naive Bayes, and Joseph he did some write up on the forum here. So he agreed to do the presentation. I'm not sure whether he's in here at the moment. Is Joseph in? I think he's in. So what the plan is, he agreed to do a bit of a presentation on it. So I thought we'll start from a recap. Lesson 11 is more of a recap with the one new topic Jeremy has introduced, which is embedding, and then we have another presentation after this. So that will be nice to get more from the fellow members. Let me check. Hey, Joseph. Okay. Perhaps we can discuss a little bit more once he comes in. We will get going. Okay.
Well,
so
yeah, I'm sorry I'm late.
I mean, no worries at all. Yeah, fantastic. Yeah. So there is. You can share.
Yes. Let's see.
What I will do is I'll stop sharing.
Okay.
And then. Okay, I have stopped sharing. You can go ahead.
Okay. Let's see what it comes up. So I have
Sure.
this screen. I don't have it. Hold on. I have to move.
It's all right.
Okay.
It's usually sometime hidden below.
Yes,
Just,
I think I found it.
okay.
Yeah. Oh, is it
Yeah. Yeah.
Are you seeing it?
Yeah, we can see it.
Okay, great. So, so I guess last time we were talking about in our meeting last time we just mentioned the naive Bayes classifier because it occurred in one of Jeremy's videos, and I just thought I would write it up a little bit so that everyone would sort of see what its underpinnings are. And I have to apologize because we're used to top-down thinking in this class, but this is definitely a bottoms-up. After we do this, then I think Michael gave a nice link to a Google Colab site where you can actually do some hands-on work with a naive Bayes classifier. And I also have a link at the end of mine that takes to a tutorial like that. But mine is just going to develop sort of the underpinnings of it. And apologies to those of you who already know it. So the starting point is Bayes' rule. Hold on, let me, I have to close my door so that other people in the house won't be disturbed. So the starting point is Bayes' rule, which is just, it's really a statement about conditional and joint probabilities. So I wanted to develop that, and that's sort of the first thing. And then from there, we can build the Bayes classifier. So you start out with the idea of joint probability that you have two events, A and B, and that the probability that they both happen is the joint probability of the A and B, and that's this notation of P of A comma B. And then the second thing is the conditional probability, which is what I mean by P of A bar B. That means the probability of A happening given that B happened. Does everybody get that? So that's a conditional probability. And so whenever you see a bar like that, you just think in your mind, given. So probability of A bar B is probability of A given B. And sort of a practical way of thinking of it is if you have a box full of red cubes and red balls and blue cubes and blue balls, and you know the number of each one of these items, you could ask for a conditional probability, like the probability that it's red if you know it's a cube. That would be the probability of red given that it's a cube, something like that. So it sort of restricts the number of things you have to look at. So you know, you look at, so probability of A given B, you look at all the things all the situations where B is true, and then you count the number of situations where A is also true, and that ratio is the probability of A, is the conditional probability of A given B. So with that, the first equation is just follows directly from those definitions. The probability of A given B, sorry, the probability of A and B is the probability of A given B times the probability that B has occurred. And so that's a general statement. And then you can also look at that equation and turn it around a bit by interchanging A and B, because there's nothing special about the order of A and B. So if you rewrite that equation, probability of B comma A, that's the same thing. Probability of B comma A is also the probability of A and B happening at the same time. And just by interchanging A and B in that first equation, you get the second equation, probability of B given A times the probability of A. So both of those things are the same, so I can just equate the right-hand side. And that's the statement, the third equation there, which is this one. And this is basically Bayes' rule. That's all it is. It's basically a statement about joint and conditional probabilities that follows from their definition. So that's it. That's Bayes' rule. And from there, we can go on to build a Bayes classifier. If you have a data set of n data points, let's say, and each data point can be classified into either of m classes, then the problem of building a classifier is really related to that conditional probability, the probability of a class given a data point. That's what you'd like to do. You'd like to have a classifier that takes as its input the data point and tells you the probability of what class, it breaks down what the probability is, what probability to be.
You're breaking up, Joseph.
The class,
Hello, Joseph, you're breaking up. Is this with?
Is everyone?
No, I think you are breaking up. At least for me. Is everybody else heard him fine? Or
no, Joseph, I can't hear you. The sound quality is very, very bad.
Yeah. Joseph looks like
we lost the connection with him, I guess.
Yeah. I think probably he's gonna reconnect. Let's give him a minute or two.
Am I back?
Yeah, you're back. Yeah.
Okay, I shared my screen again.
Yeah, please.
Okay, everybody see it? Okay, so now we're just applying this statement of conditional probability to define a classifier. Because if I can calculate the probability of a class given a data point, that's basically a classifier. That's basically you can predict the class given a data point. So that's this equation here, which is just it's just a rewriting Bayes' rule. Instead of A and B, I have C for class and D.
Okay, sound quality again, sound issue, Joseph, unfortunately. You're breaking up.
Yes,
Joseph is breaking up. That's a Bayes classifier. Okay. Okay, well, maybe we should just continue with someone else then. Or continue the meeting.
Yeah, at least I think it says Probably the internet. You're gonna give maybe a last go.
Can people hear me?
Yes, now yes.
Okay. I'm sorry. It must be my connection, and there's nothing I can do about it.
Exactly. Yeah.
So
No worries.
yeah, if I drop out next time, just feel free to continue the meeting. Anyway,
Sure.
and I'll tune back in. Anyway, so the names for these terms are on the left-hand side. That's called the posterior, the P of C given D, and P of C, the probability of a class, is it's called the prior. It's you look at all the data points and separate them all into classes, and then in your training set, and then you figure out the probability of data point being in any class. So that's easy to calculate from your training set, the prior. The likelihoods are more difficult to calculate, but still can be done. That's the key thing, is calculating the likelihood, which is the probability that that a given class could give rise to a data point D. Probability that we would observe the data point D if its class, if its class were given. That's called the likelihood. And then the evidence is the denominator P of D, the probability of that data point could occur in nature, irrespective of class. That the denominator is something we generally don't have to worry about, because it's sometimes can be calculated but often can't. But P of D doesn't depend on the class. It's the probability of the data point occurring irrespective of classes, and so it ends up acting just like a proportionality constant, and we don't really care about it, because what we're really interested in is the relative ranking of the left-hand side, just basically how large they are, because we would, in a decision, if we adopted a decision rule, we would probably do something like adopt a class with the highest probability. So you don't really care what the probability is. You just care that you got the maximum. All right. So let's see. So then, just to summarize, to apply the Bayes classifier, you would compute the posterior, which is the left-hand side of the equation, and then you would apply a decision rule, which would usually be the maximum a priori posterior rule to predict the class label. You just basically find the maximum. You predict the class probabilities for each class for each data point, and then you okay. In other words, given a data point D, you predict the posteriors P of C given D for each of the classes C, and then you choose the one with the highest value. That's the map rule. To assign the label. So the naive Bayes classifier just goes one step farther and says, let's assume that the feature values of a given data point are all independent. In other words, if you have like two features like height and weight, that suppose you're classifying human beings by their height and weight, or then the naive assumption is that the features of values are independent of each other. That is, that the height, for example, would be independent of the weight. And obviously that's not true for humans, but it turns out that you can sometimes make this assumption, even if it's not true, and still get away with it and get a good classifier. So things simplify when you make that assumption. The likelihood becomes a product of likelihoods, of independent likelihoods. So, in this case, P of x1, x2, xm would be given C would be the probability that you would have all the feature values given a class, given the class C. So, for example, in a simple human being classification problem, the class could be man or woman, and the features could be height and weight and age or something like that. So the naive assumption that likelihood into a product of here, and I neglect I just treat the denominator as a proportionality constant. Then I have this proportionality here. And the comment here is that these likelihoods can sometimes be small, and if you have a product of many.
Sorry, Joseph, can you go back maybe a minute back? There was a connection issue. Maybe just repeat the last step, please.
Sure. So you want me to sort of go over this equation?
Yes, please.
Yes. Okay. So we're making an independent. We're making an assumption that the features values are independent of each other. So so that the probability of having a given set of feature values given a class becomes the product of probabilities of having the independent feature values. Does that make sense? This equation here?
Yeah.
Yeah. So now I'm going to substitute this equation into the base classifier expression here. I'm basically going to substitute for this term here, which we just said can be written this way. And then when I do that, I have this equation. So this is and then the comment here is that this is, here you have a product of likelihoods, and the likelihoods can be small, and there could be many of them. So this equation is subject to underflow error, so you don't really want to use it for practical computation. Instead, you want to take the logarithm. And what you get when you do that is the next equation, and that's the naive Bayes classifier right here. I've neglected the proportionality constant because we don't really care about the offset. The proportionality constant becomes an offset when you take the log. And if we're just looking for the maximum of the conditional probability, then you don't care about that offset. So now this is the Bayes classifier, the naive Bayes classifier here, in a form that you can actually use it. Let's see. You're trying to compute the likelihoods, and you ask for what's the probability that it has a certain value, that some feature has a certain value given a class, and what if there aren't any? Like in the example of balls and cubes, what if there aren't any red cubes? Then one of these likelihoods would be 0, and then the equation would blow up because you'd have the log of 0. So there's a trick that people use to get around this, and that is that they add in the ratio, when you calculate a ratio of you're counting objects in a certain class, and then you're counting the number of objects that have that feature, and you're taking the ratio of those two things. You just add to the denominator, and that way nothing can blow up. So you protect yourself against that, and that's a variant of Laplace smoothing. It's one of the ways you can do that. So so that's it. That's the Bayes classifier. Let's see. And there's some comments about it. It's sort of unreasonably effective. Sometimes it shouldn't. I mean, sometimes it works when you don't think it should work because the assumption isn't true. The naive assumption isn't true, and yet often you find out you still get a good result. And there's actually some mathematical work that that says why that happens, and I've linked to I think I've linked to an article that discusses that. So what are its advantages? I was trying to compare its advantages and disadvantages, and I found there's a lot of advantages. Mostly people have used it in the beginning for problems where you don't have a lot of training data, because it's found that it can generally achieve better results than other classifiers. And the reason is partly because it doesn't overfit very much, and that's because of Bayes' rule. Bayes' rule tries to predict what should be true given what you already know is true. So it penalizes. You know, you have you have some things that you know are true, and it penalizes if you try to go beyond what you already know is true. So the other thing is, or other features are that it's very quick because you're basically just computing analytic formulas for the priors and likelihoods. There's no iteration, there's no gradients, there's no updating. So it's quick. It doesn't require a lot of memory because you don't have to have all the data in RAM at once. You're just using summaries of the data like ratios and and the likelihoods and priors. You don't need to have all the data in memory at once to compute those things. And then again, the CPU usage is modest again because you don't have to compute it's not very compute intensive. You don't have to compute gradients, matrix products, or anything like that. Another good thing is it scales linearly with the number of features and data points. So it can easily be extended to very large data sets. And if you have new data, you can easily update it with not too much computation cost. It's just because if you think about it, if you get some new data, all you have to do is recompute the priors and the likelihoods, and those are just analytic formulas, and they're quick. And then another good feature is that if you have missing features, then it's easy to handle those, because you just the result turns out to not depend on missing features. So it's easy to predict without the feature that's missing. Disadvantages are that it can't incorporate any feature interactions because of your assumption is that the features are independent of each other. So that could be a showstopper in cases when you have highly nonlinear models that have feature interactions. Let's see. And then for regression problems, for continuous data, it may be difficult to calculate the likelihoods. And binning is one way you can do it, but that's not optimal because you lose information, and also the result could depend on how you chose the bin. So that's really not usually a good idea. And if the features are not normally distributed, that's the assumption in naive Bayes. If they're not distributed like a Gaussian, then you can run into trouble. So, and also the performance is sensitive to skewed data. If you don't have if your sample doesn't represent properly the proportions of the different classes, then your priors are going to be all wrong, and then your performance could take a hit on that if you don't have the good priors. So that's it. That's the Bayes classifier, and I think if you wanted to use it, you'd probably want to go to one of these references at the bottom, or the one that Michael put up. This one here, the second one, actually goes through a really simple example where it shows how to calculate all the priors, the likelihood terms, and so on a very simple example. So this second one is a good one to look at next. And that's it.
All right, that's great. Thanks very much, Joseph. Any question, anybody?
Okay, now how do I relinquish? How do I?
I have a question.
Yeah.
And the question is stuff I always ask with. Sorry, can you hear me? Yeah.
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 So good. With Bayes, where do you get the prior from?
Well, in this case, the prior is just counting. In other words, if you have let's say you're doing a sample of people and you're measuring their height and weight, and you're trying to predict whether they're male and female. So the two classes are male and female, and the prior is just the proportion of your sample, the proportion of people in your sample that are male, and the proportion.
Okay, I see. Wow. Yeah, that's really simple. Yeah. Okay.
Yeah, so it comes right from the data.
Okay, so it's basically data dependent in this case.
Yes. Any other?
Okay, anybody else?
Yeah, I would like to ask a practical question. Naive Bayes, is the choice to make in some kind of problem, or it's in some type of problem better than, for example, random forest, or not?
Yeah. So the question is when should we use naive Bayes? And as far as I can tell, there are several use cases. One is when you don't have a lot of data, when you don't have a lot of training examples, because then it's reputed that naive Bayes can usually get a better result than other classifiers. And another use case is when you have a lot of data. You can use naive Bayes as your baseline. You can write the naive Bayes model. It's easy to code. You can run it, and then you get some performance. I have a benchmark, and you can try the random forest, and you can try gradient boosted trees, and you can try neural nets and see what it beats it. there are some sometimes when naive Bayes can even beat neural nets because because neural nets would require too much compute, and naive Bayes is very light on compute power, even for large data sets. So the use cases then, small number of samples or a very large number of samples as a baseline.
Okay, thanks.
Yeah.
So I would just like to take the opportunity to thank Joseph again. It was very interesting. It was very enlightening, at least for me. So thank you very much for explaining this in such a concise and good way. Actually, it was like I've read about naive Bayes for quite some time now, but now I think I have a little bit of a better understanding, or even can conceptually understand it. So that was very nice. Thank you very much.
Yeah, sorry I didn't have time to put in some working examples. That would have been nice to have like a coded example and actually do it in the notebook, but that would be the next step. And I think Michael put up a link that allows you to explore that in Google Colab.
Yes, that would be even better, but I think your presentation was very nice, and you're right. You understand it even better if you use it practically, yes.
Okay, so thanks. I'm going to turn over the sharing back to the moderator.
Sure. Thanks very much, Joseph.
Welcome.
Okay. Let me go back and share my screen, but it's give me a second. I'm not able to find. Oh, I can. What's that? I was trying to find the presentation to share. You can see my screen now?
Yes.
Yeah, okay. So thanks for that, Joseph. Now, from the naive Bayes to embeddings, I think one of the topic discussed on this lesson 11 was the embeddings. And we have a group member, Mahesh Khatri, who has done some presentation before in a DL group. I have links for his previous presentations. However, he's going to give us a really nice idea about what the embeddings are. So I'm gonna stop sharing, and I'm going to give control back to Mahesh, so that you can start on your own time, Mahesh.
Yeah, thanks, Padia. 1 second. Let me just. Okay, can you see my?
Yeah.
Yes.
I can see it. Yes, thanks.
Okay, Padia, how much time do I have? About 20 minutes?
Yeah, you can take 20 minutes. That's fine. I think this is a very important subject, and then you explained very well. So take your time.
Okay, and I just want to have a quick poll. How many people were there for the earlier two presentations that I did? The last one, the presentation which I'm showing right now, was in mid-November. So how many people were there? Any feedback or?
Mahesh, I have a question. Is this presentation already on YouTube? Because I think I've seen it on YouTube.
Yes, yes. What I'm going to do is I'm not going to cover the entire presentation. I will just cover a portion of the presentation because it helps me go through it in a structured manner. So, or if you have any questions, I could take that and then we could proceed. So,
yeah. I did watch I wasn't present that day, but I did watch the video of the deep dive, as well as the introduction you made on, I think, 14th of July.
Yes, yes, it was 14th of July, yeah. So what I'll do is this deep dive presentation, which I did last time, I'll just quickly go through some of the basic points in that, and I'm assuming that most of the people present now have not really seen the presentation. So just pardon me if there is repetition and then I will skip the, I will go ahead.
Not at all. You just go ahead with your flow, Mahesh.
Okay, fine. So this deep dive essentially was a coverage of 3 different papers. And what I will do is I will not cover the papers today. I will just cover the basics of entity embeddings. So essentially 2 questions: what are entity embeddings and why are they important? Now, entities from a layperson's perspective are simply nouns. You know, anything that you can describe as a noun is an entity. And in mathematics, you know, embedding is a containment of a mathematical structure within another instance. So let's say I have a noun, which is my entity, and I have a mathematical structure, which is a single dimension array of, let's say, d elements. So I could have an entity called as store, which is represented as an array of, you know, as a single array of certain number of dimensions. I could have an entity such as a product. I could have an entity such as a supplier, customer. The essential point is that these entities are being represented as vectors. So essentially, what is the importance of the entity embeddings? Two features. One is that, you know, domain knowledge is the need for domain knowledge leading to feature engineering gets reduced considerably. In fact, you know, in the presentation which was made at the Kaggle competition, the people who won the third prize, they essentially were people who had no knowledge of the retail sector. I'm talking about the Rossmann stores competition. In fact, the first and the second prize winners were people who had very detailed knowledge of the retail sector. So this is the first point, is that the domain knowledge gets reduced. And the second is that it is independent of any specific AI or machine learning method. In fact, in one of the papers which I have referenced in this presentation, embeddings was used with different machine learning techniques. It was used with random forests. It was used with, you know, gradient boosting machines. And the authors have shown that essentially wherever the embeddings were used, it gave rise to better predictions. So I'll start off with word embeddings, because it started off from, you know, the whole concept started from word embeddings in natural language processing. So essentially the concept is the same. A word is a vector of d elements, n1, n2, n3 to nd. These are d different elements. So a cat, you know, and a mat are 2 words which are represented as vectors. What is actually happening is the embedding function w is a function which is mapping the word to, you know, very high dimensional vectors. This is a nice article which I have referenced, which is Christopher Ola's blog, which you can refer, which has a very nice explanation of word embeddings. And what it is actually doing is, it is getting initialized randomly, and after initialization, it is learns these values to perform a particular task. So let us see what the task is. So there are 2 different tasks which I have seen over here. One is, let's say I have a task to predict the sentence validity, whether a particular sentence is valid or not. And I could have another task which is to analyze the sentiment of the sentence. So I have shown a diagram of a deep neural network. Inputs on the left hand side with the input layer, the predictions, and multiple hidden layers in between. So let's say I have a sentence called "the cat sat on the mat," and this is a valid sentence. So the prediction is 1. I have a sentence which there is a mistake. It says the cat sat song on the mat, and this is an invalid sentence. So the prediction is 0. So through the process of, you know, the back propagation and the gradient descent, for both the valid and the invalid predictions of the, you know, sentences, the embeddings essentially get computed and you get certain amount of values which get reflected in the embedding itself. So even though this slide looks very complex, it's not really. Wherever I have the function R is actually the deep neural network, which is taking in the different word embeddings of each of the word, and the top sentence it is showing a 1, the bottom sentence it is showing 0, and with the result that after the task is completed, you get an embedding calculation which is as shown over here. Now it's important that these embeddings which have been calculated are only for the task of sentence validity. If I have another task, let's say called as sentiment analysis, you would have different different calculations of the embeddings. So it's important to get the concept that different tasks will lead to different embedding values for the same entity. So this has got meaning in the context of information systems which are there in the real world in terms of enterprises. For instance, you could have a concept, or you could have an entity called as a customer. Now the accounts receivable system, which keeps track of how the customer is making the payments on time, that could calculate a different set of embeddings for each customer. Then say a system which is calculating the customer satisfaction rating of a customer. So the embeddings for that customer entity would be different. So essentially what word embedding does is it leads to word mathematics, as has again been shown in the particular block. The relationship between man and woman is the same as the relationship between uncle and auntie or king and uncle. And these are also useful for understanding, for instance, geographic concepts. The capital of Germany is Berlin, which is also the same as as Moscow being the capital of Russia. So the link which I have shown over here, which is a TensorFlow link, which talks about the vector representation of different words. The embedding also works in the context of verb tense. So walking and walked relationship is the same as the relationship between swimming and swam. Again, these are all concepts which the neural networks have learned based on the generation of mathematical values for each of these different words which have been shown over here. So essentially what have we said? We have said that word embeddings lead to mapping of individual word values into multi-dimensional space. Any questions at this stage? Can I go ahead?
Yes, please.
Just one question. What are the typical dimensions of these spaces? Like, what is a good dimension for a word embedding? Is it 10? Is it 100? Is it 1,000?
Sorry, I'm not able to hear the question. If you could put it on the chat, I could answer it. I really I could not hear it.
Oh, I'm just asking about the dimension of the word embedding.
Yes.
Should it be? How do you choose that?
Okay. In this particular presentation, I have shown how in each of those different papers which I have represented, they have used a certain calculation. Jeremy Howard gives a very simple explanation. He says the number of cardinal values that you have in your variable, that plus 1 it should be your embedding size. For example, just to give an example, if you have day of the week, there are 7 days in a week. So you add 7 plus 1, which is 8, and you divide by 2. So Jeremy says that the size of the embedding should be 4. Okay, but there is no hard and fast rule. For instance, in one of the papers, they've used an embedding size of 10. In the YouTube paper which I have referenced in this presentation, they say that the embedding size should be the logarithmic of the, it should be a proportional to the log of the number of values that you have. So my guess is that people are just experimenting with whatever values have worked for them. So, but there is no hard and fast rule. In fact, in
Okay.
this sorry.
Yeah, thank you.
Okay, okay.
I have another question in the beginning. You mentioned that the sentences are judged as valid, and my question is, who is doing this? Is it like this is the ground truth that are provided by humans, or?
Yes.
Yeah.
It's essentially, it's a classification problem. So
Okay.
you have a label, which says sentence is valid or invalid.
Thank you.
So, yeah. Can I go ahead?
Yes, please.
Okay. So we looked at word embeddings. Now let's look at, the embeddings as far as the real world entities and events are concerned. So, when we talk of, data types, we essentially have data types of entities as represented in systems. We would have, let's say, categorical, and numerical. Now, again, here, the terminology varies from paper to paper. So if you read certain papers, they'll give a different terminology, but most of them have agreed on the terminology called as categorical variables and numerical variables. Now, categorical variables are essentially which indicate membership. For instance, a person gender, male, female, marital status, married, single, divorced, citizenship type. Uh, so, and numeric would be things which for which actually we have numeric values, which are there in the which are there in the data. So I've taken a simple example in this presentation where I just look at a person's record consisting of these columns. So here marital status and gender are the categorical variables, age and weight are the numerical variables, and the entity embeddings are really for the categorical variables only. Why do we say that? Because essentially what we are saying is that my neural network only understands mathematics. It only understands numbers, numbers go in and numbers come out. The input numbers go in, and your predictions come out in terms of certain numbers. So let's say if I have marital status, I could do simple label encoding as 0, 1, 2, 3. I change my marital status into 0, 1, 2, 3. But essentially, if I just look at it from pure mathematical form, 3 will have a weight which is 3 times more than single. So from a DNN's point of view, it would take, it would multiply, the weight for widowed as 3 times as that for a single person. So a possible solution will be that, we do what is called as one hot encoded vector binarization, where essentially we replace, the first position in case of married. The first position gets a 1, remaining all gets 0. For single, and so on. This was used earlier in many of the neural network calculations. But again, there were certain problems with this. There were problems of memory computation. There were problems of arbitrary differences between levels. So entity embeddings has also been used instead of one hot encoded vectors, because if you look at it mathematically, they are the dot product of the one hot encoded data and the learnable weights. So if this is my, R rows by a single column vector, and if I multiply this by different weight dimensions, so I have, multiple column weights and one single row. So essentially, if I see my first value 1 will have the, matrix as shown on the right hand side. If I take the second, where my second position is 1, this will be the matrix, and so on. So essentially what even Jeremy has mentioned this is that these entity embeddings actually act as a lookup row for specific label encoded values of the categorical variables. So, so just like word embeddings, we have entity embeddings which are used to map discrete values into a multidimensional space. So instead of marital status and gender, being just single values, they get, each of those instances get replaced by a certain by a single dimensional array. So let's look at the actual data storage. So you would have marital status, let's say, and gender both getting replaced by, each of those instances getting replaced by a vector, a single dimensional vector of of different dimensions. In this case, let's say marital status, embedding size is 4. There are 4 values, W11, W12, W13 and W14, and your gender has got just 2 values, G11 and G12 for each of the values. So these are referred to as the gender entity embeddings and the marital status embeddings respectively. Now if you look at the now this same concept, Google talks of as, in TensorFlow it's spoken of as a wide and deep model, where wide is the categorical variables and deep are the continuous variables. And I've shown the link below of there is a nice tutorial where it talks about wide and deep learning, where essentially for every data that you feed into your model, you have to identify the categorical variables, you have to identify the continuous variables, and then based on that, it treats both these. If this particular model treats both these variable types separately. So essentially what happens is, now this was the papers that the 3 different papers that we had covered, where so you will have in your inputs, you will have both the categorical and the continuous variables which go in. So categorical variables, as I mentioned, would be the entity embeddings and different libraries. For instance, here I have shown the Fast.ai library has got support for the categorical variables. For example, in one of the Rossmann stores example which Jeremy has shown, all the dates values which are there get actually replaced by a function called as add date part. Now add date part is a very rich function because it looks at that specific date and it creates a different series of embeddings for the dates. Let's say, is it the first date of the week? Is it the first Sunday of the month? Is it the last fortnight of the week? Is it the fortnight before Christmas? All those kind of rich relationships are captured by this add date part function. Similarly, if I look at TensorFlow, TensorFlow has got it has got a facility called as TF. TF is TensorFlow. TF, feature column categorical column with vocabulary list, is a function. Similarly, it has a different function called as feature column categorical column with a hash bucket. So again, these are very rich functionality which is built into the libraries to help generate the rich embeddings which are then used as inputs for the networks. Now these papers that I covered, I'll just quickly go through them because these only focus on the entity embedding parts. What I've done is, even though these 3 papers are different, I have tried to use a simple terminology which is consistent across the 3 papers. So you can probably go through it and ask me any questions that you have. You could, I will answer them on the chat or on the Slack later on. So this was the first paper that we looked at, which was the neural networks for taxi destination. This was Yosh Bengio's paper, where we had the categorical variables, which were the embeddings. For instance, here, if you see, for a taxi booking, the taxi ID, the taxi stand ID, client ID, each of these, there were embeddings for that. I mean, there were embeddings for hour of the day, day of the week, week of the year. And then you also had the continuous variables, which were acting as inputs to the network. Similarly, this was the lessons. They got the first rank, and it was used across different machine learning algorithms. It was also used in RNNs. It was also used in multilayer perceptron and so on. Second paper was the Rossmann sales paper, where again embeddings which were used over there, and here again they've given the advantages that they were used it across different machine learning methods, and they were the only team which had got no domain specific feature engineering. These guys didn't know anything about retail, but yet they were able to get the 3rd place, and the model was very simple. It didn't have any. The first and second place winners used an ensemble of models, whereas these guys only had a single model. The third is a very large, YouTube network consisting of a billion parameters, billion input values. And here they actually have 2 networks. It's not just one network. There is one network which is used for the for generating of the YouTube videos that they would like to show you. And the second network actually ranks the YouTube videos, and both these networks use very extensive entity embeddings which are generated from multiple sources. It is not just one source. So they look at your what videos you watched, what searches you've done, from where are you, which part of the world are you logging in, what are your device types, and so on. And then based on that, what are the languages that you have looked at, and it generates again, it uses embeddings extensively. I think this paper came out a year later than the original paper, but I think based on what they're talking about, they've been using embeddings for a lot of much more longer period of time than what is generally acknowledged. So essentially this was it's a large system, so that's the reason why it was important. And an important point that they make over here is that these embeddings are used across the entire network. So they talk of sharing embeddings, which I think is a lesson. For instance, I mentioned it in my talk also. Twitter just released a paper a couple of months back where they have an embedding store. So essentially, everybody in Twitter can use that store and use those embeddings for their own. Different departments use it for their own, own network and own recommendation systems. This was a question which somebody asked: what should be the size of the entity embeddings? So essentially, this is what Jeremy Howard says. It should be half the number of values plus 1 with a maximum of 50. In the taxi destination paper, 10 was the size which was used. Again, in this paper, in YouTube talks about it being proportional to the log of the number of unique values or cardinality of the entity. Okay, it's used almost most of the organizations, and Jeremy feels that it has got huge opportunities to solve problems which have not been solved before. So essentially, we looked at it embeddings from two perspectives. We looked at it from word embeddings. We also looked at it from the from the real world data types, categorical, and as an evolution of the one hot encoded vector. Then essentially there is another way of looking at it, is that is from the real world entities and systems. See, what happens is, if you talk to any knowledgeable person in any organization, intuitively they can tell you what works and what doesn't work. I look at embeddings as a way of mathematically representing that knowledge, which is tacit in the experience of individuals. So I see this as a good area in terms of work ahead, and I think there'll be much more to come in this field. So any questions? I think I finished my presentation very, very fast. So any questions, anyone?
Okay, if there is no question, then thanks a lot, Mahesh.
Okay, thank you. I'll stop sharing this. Yeah, 1 second. Yeah.
Okay, that's great. All right, we have 6 minutes left. I am going to share back. Right. Okay. So these were the presentation, and then I have just 2-3 more slides. It's just going through flow what Jeremy covered in this lesson. This is something interesting, like here, like in a PyTorch. Anybody try to do this .grad attribute or .backward method to uncode the multilayer function? Any view on it? This is, he started reviewing this multilayer functions, how they works, so and so forth. And I think this is what he was explaining, that it's very, very difficult to do by hand, but you have in a PyTorch, you have something called a dot grad attribute and a dot backward method. And we tried it. I haven't.
I was using them for the CAM heat maps. Basically, you play around with the gradients as well. But that was not related to this lesson. But to do this CAM activation maps, you have to record the gradients as well. If you're talking about that.
So backward with kind of keep the functions, so to calculate the gradients, right?
Yeah.
And the grad is just for single calculation. Is that how to understand?
No, if I recall correctly, grad is just the variable where the actual gradient.
Okay. All right.
And then basically you have to be careful that you have to zero them, because otherwise they would just accumulate over time.
That's right. Mm-hmm. Thank you.
All right, I'll move ahead to the next slide, which is just simple cross entropy. I think he was using cross entropy, and this is just like a loss function, like a root mean square, but specifically designed for classification. And that's the if statement. Interestingly, he asked students to write. That's the if statement on it. Any take on it? Anybody wants to have a more discussion on this function? What cross entropy is? Or somebody wants to explain further on?
Yeah, I mean, the question is, I know what entropy is, but I don't understand what cross entropy is. So if anyone would chip in to explain that, that would be great, actually.
Anyone want to take a shot at it?
I think cross entropy is just showing, excuse me, it's just taking into account all the classes. I think it's actually the same thing as entropy. It's just adding the entropy of all the classes. Because each term, you know, entropy is about a class. So if it's a simple binary cross entropy, then it's, you know, the probability, it's the entropy associated with ones or zeros, and you add them together. If it's a multi-class problem, then there are, you know, if there are m classes in the multi-class problem, then the cross entropy has m terms, and each term is the entropy of one of the classes.
Okay, now I see. Yeah, right. So would you say that it's actually closely related to entropy?
Yes. Yeah.
Okay. Yeah, thank you very much.
Okay, and so I'm going to move on from cross entropy to, I think, this is the function which NBSVM++, which I think it's Jeremy's invention. Is that it? Him saying they develop. I think this is the library. He showed it here, and then embedding come in here. That's it. He mentions. And interestingly, there was a good discussion on this adjustment 0.4 as a constant adding, I think it was here. So anybody want to chip in? What's this all about? NBSVM M++, any issue?
That's naive Bayes support vector machines, I think, right?
Yeah. He said
Yeah.
plus.
Plus, yeah. I don't know what's that plus.
Yeah, I think plus is his. I think that addition of the embeddings plus I think this adjustment weight, where he was explaining that that W scare is the what it's called. It's not coming into my mind. There was some summation of W scare weight scare where the it's not coming to my mind. anyway, anybody wants to explain any further on it or any discussion on it?
Can you hear me?
Yeah.
Okay, so my question was about the
Sorry, you're not clear. There is a lot of background noise.
Once again, if I won't succeed, then next time. My question was, for example, we have an embedding that embed our vector into four-dimensional space, and this is the kind of projection into hyperplanes. But afterwards, we want to project into five dimensions. Will it change the projection into first 4 dimension, or it will just add additional layer of knowledge like about the domain? How will it change the structure of the embedding of particular vector?
No, I think you are saying originally you have your embedding will be of 4 dimensions, right?
Mm-hmm.
And then you are saying that you will train it further, and you will add one more dimension to make it 5 dimensions.
Yes. How will 4-dimensional embedding will relate to the 5-dimensional embedding? Will be it like expansion of the matrix that project the vector of words into some embedding or something else?
No, see. In one of my slides, I had mentioned that if you look at the word, let me take word embeddings as an example. There, Christopher Olo talks about 400 to 600 dimensions for every word. So essentially, what every dimension is doing, it captures a certain attribute of the entity. In one of Rachel Thomas's lecture on entity embeddings, she talks about, let's say, cat. Embedding for a cat and embedding for a dog. Okay. Now, one of the dimensions in each of the cat and the dog dimension, let's say it could refer to size. One dimension could refer to attribute, or it could refer to the youthfulness. So what we really have to look at is what are we trying to model in the real world? What is the kind of entity characteristics that you are trying to capture. So so whether it is 4 or whether it is 6 or whether it is 8, over a period of time, once your network has been trained to generate the embeddings, it will over a period of time tend to give each of those dimensions will represent something about the entity. Have I made myself clear? Are you
yeah, almost. But I would like to clarify the question in terms imagine we have four-dimensional embedding of the cat and dogs, and
yes.
The first dimension is like a category like animal, so it's like 1 or 0. So cat is animal and dog is animal.
No. Sorry. I'm sorry. No, that will not be represented in the, that will not be represented in the embedding itself, because see, you will be capturing certain very specific characteristics where their assumption is already there that these are animals. It's not like object oriented programming where you have a super class and a subclass. The embeddings are actually capturing very fine characteristics of the entity. So
but isn't the case that we can interpret sometimes the embedding of the word having some particular sense, for example, the queen, the king that you showed before, it's like female, for example, that is royal, that is related to some country, and so on. So
yes.
And when we add another dimension, we could put the embedding that would nullify the previous, and change the all the structure of embedding. And after this change, won't be model changed drastically. So I mean, we have the model that is predicting quite well with the 4-dimensional embedding, and then we change the embedding and have it and all our weights and all the stuff in the model will change drastically, and we have just a totally different model with different prediction and so on, adding only one layer of embedding, like only one dimension of embedding.
Yeah. See, I'm not sure whether the model will change drastically.
Mm-hmm.
You know, my assumption is that the fifth dimension that you will add will find, and you know, it will represent a new characteristics of the cat or the dog. It may not change the previous 4 embedding values very drastically. You know, I gave the example of a customer. I said, for instance, I mentioned the example of Twitter. Now, Twitter uses different embeddings for different tasks, and these embeddings are shared within the organization. So, you know, you could have the fifth dimension, which may, you know, it may change the values of the previous 4 dimensions, but it may, according to me, it may not change very substantially. It may enhance it. It may not change very substantially. I could be wrong though. I mean, it all really depends on the model and what are you trying to represent in your model.
But it just was a question of a general interest. Thank you for your answer.
Okay, thanks.
Okay, anybody else want to share any stumbling block, any interesting read, anything, any question?
So next week is our last meetup.
Yeah, that's correct. Yeah, that's Sunday, bang on time.
Yeah, and that's about the completely Rossmann project or competition, and also about the ethics and the machine learning. And then what's happening on deep learning study group, we're forming like a weekly meetup, not that very structured. It's just to practice on what we learned. So what we could do, we could kind of join that meetup, and because deep learning is also machine learning, it's basically the same thing. So we could continue meeting weekly and presenting some interesting ideas, projects, or something like that. Just an idea what to do after we finish next week. If you're interested in that, yeah.
Yeah, absolutely. And it's on Saturday, 5 p.m. GMT. Is that correct, Michael? Yeah.
Yeah, I think so. Yeah, it's 12 o'clock my time.
Same time Saturday. Yeah.
Yeah, same time. Yeah,
same time, but just Saturday. Yeah.
Yeah.
So what we I'll share that poll. So what we're looking, because it's like 12 weeks, we're planning to do before the part 2 of the deep learning course starts. We need some people to host some meetings. We want to share as we did with this study group, so it's not like one person needs to be like every week. If you cannot make 1 week, it's also fine.
Makes sense.
So I'm going to post a poll if you are willing to host a meetup. Like to host, I mean, open the call, and then the rest is up to you, basically. So you need to be present. That's the kind of thing that you need to do. And then so if you're interested of participating or hosting one meetup here and there, then just put your name on the poll, and then we go from there.
All right, thanks, Michael.
Thank you.
Okay, so that's pretty much it. We have it. I'll share this slides on the Slack.
Okay, thank you.
All right.
Fantastic.
Okay,
thank you.
All right, guys. Thanks so much. Thank you all.
Thanks. Bye.
Thank you.
Bye.
Thank you.